proceed, our next contestant is Mr. K. Hok Hing from Sealing Primary.
Okay, good evening, and actually I'm feeling so scared up here. Okay, here goes. I have a nest for the ping pong balls. The 5 ping pong balls are here. In front of you here would be 2 dumbbells, but they are not dumbbells today. Okay, they are my very own catapult of science. All right, I have these rubber bands. Okay, 5 of them across the 2 dumbbells, and I have a beautiful spoon. Okay, which I'm going to place in between the elastic bands. Okay, and I think I am kind of ready. Alright? Okay, so I have ping pongs. Okay, and I have a catapult there. So this will be my presentation for today, ping pong catapults. Okay, I'm presenting on the topic of energy. So today we'll look at the changes of energy. And we'll do a little bit of process skill. Okay, so we'll study how distance flown by a projectile, so in this case a ping pong ball. And the variables involved here will be the number of rubber bands. Okay, we will need this graph. Okay, we'll take the rows to be the units of distance. Okay, rows from the counter. Okay, we'll be working with rubber bands in 5, 10, 20, and 30. Okay, I will need a volunteer. So can I have someone pretty? Miss, can you help me out for this demonstration? Okay. Yes. And Miss, your role is very important. You just have to sit pretty and be the marker for row number 1. Okay, row 1, okay, row 2, row 3, and so on. Okay, audience, I will need your help, okay, to let me know how far the ping pong ball actually travels. Okay? We're using rubber bands, of course, wonderful material made of rubber. Okay, rubber bands rubber is actually something elastic. Okay, would you know what that means? Okay, would you know what I mean by saying that rubber is elastic? Anyone? Okay, it stores energy. Actually, I've gone one step ahead of me. Okay, something elastic is something that it can be stretched, something that can be pulled, and it will return to its original shape easily. Alright, and being so wonderful, it therefore stores energy within itself. Alright, so if I pull rubber band back, and I release, okay, the energy, okay, there's energy stored in the rubber band, and this energy will actually change into other forms of energy, right? So let's start our demonstration. Okay, first we have 5 rubber bands. Okay, so audience, where did you land? Okay, row 1. Okay, so we'll keep that data in mind. Okay, so now I'll add 5 more rubber bands. I have to work fast. Okay, so total of 10 rubber bands. Okay, so ready? Okay, audience, that will be row 2. Okay, so let's put in some data. Okay, so when I had 5 rubber bands, it went up to row 1. So this is 1. Okay, this will be 2, 3, 4. So when we have 10 rubber bands, it went up to row 2. Okay, so let's increase the number of rubber bands to 20. Okay, again, I really have to work very fast. Okay, 20 rubber bands. Okay, same position. Catapult ready. Ping pong ball. If you really need to shield yourself, please go ahead. Okay, that will be row 3. Okay, 20. So row 3. And 30 rubber bands now. Okay, ready? 3, go! That's a skill result. Okay, let's do that again. Okay, let's try that again. Okay, ready? Oh, God. Okay, that will be row 2. Okay, so from the graph shown, right? Can we therefore make a conclusion? Alright, so when we actually increase the number of rubber bands, what do we actually see? We actually see an increase in the distance traveled by the ping pong ball. As for the last result, I something on my trembling hands and trembling legs, feet as well. Okay, it's actually not within our prediction. Okay, our ping pong ball, I think they are gone into the audience. Okay, so to start off with our experiment, we actually have potential energy, elastic potential energy within the rubber band. And when I release the ping pong ball, okay, it actually went flying. No, it didn't went flying. Okay, it went flying into the audience. Alright, and when it was flying, okay, the ping pong ball was actually moving. Alright, so when a ping pong ball or any object is moving, okay, there's a different type of energy. So what would be that type of energy? Okay, very good. Okay, that would be kinetic energy. So there was a change of energy from potential. Alright, so we started off with elastic potential energy. And this changes form into kinetic energy. Right, when it was released. If we do have a hard surface, you might even hear a certain sound when the ping pong ball lands, and that will be another type of energy. Okay, anyway, this is easy to build, so go home and try one for yourself and practice on your friends. Okay, thank you.
Okay, thank you, Mr. K. We can take one quick question. Is that yes in front?
That many experiments at home and anticipate the errors involved?
Not really. I actually had only one trial on this before I actually come forward. It did work well, so that's why I felt Fine. So stage fright is another story altogether.
Okay, thank you very much, Mr.
Okay, and I thank Miss for coming here. Thank you.
Mr. Tom Mingfat for Damai Satsumi.
Alright. Good evening, everybody. Just to introduce myself, alright, I'm Mr. Tom, right? So, and my name is Mingfat. And I've been attending School of Hogwarts for 15 years. And the school managed to invite me today here to look for potential wizards. Alright, so I would like to ask if any of you are interested to be a wizard. Yes, if you're interested, please come forward. Alright, so let me assess your potential. Alright, very simple. Your name, please. Wong Hong Chan. Alright, so you will see whether Hong Chan has the potential to be a wizard. Alright? Okay, very simple, Hong Chan. You just need to do some very simple tasks for me. Alright? So, very simply, okay, hold these two pieces of paper at the same height. Alright? Okay, before you do anything, okay, I want you to tell me what is going to happen when you release both his hands at the same time. The piece of paper will fall. Which one will fall faster? Same. Anybody has a different answer? Nobody. Okay. Hong Chan, show them your wizard power. One, by the count of three, yeah? 1, 2, 3. Okay. All of you may have the potential to be wizard. Okay, good. Now, let's move on to something more interesting. Alright? Okay, over here. Okay, I have all the graduates, alright, from the School of Hogwarts. Okay? Later you can come and take a look if you're interested. Okay. Now, the next thing I want to test him is this. Alright? He's going to hold one bowl in one hand and the piece of paper on the other hand. Alright? And then, now, my question is, can you do it please? Okay, before you release it. Same question. Is it the piece of paper will reach the floor first or is it the book? The book. Anybody has a different answer? Nobody? Hong Chan, are you ready? 1, 2, 3. Yes, you are also correct. Okay, you are also correct. Right. Now, this is the final one. Okay, the final one. Okay, let's see. Okay. This time, same material, one bowl and one sheet of paper, right? I'm now going to place the sheet of paper on top of it. Okay? And by the count of 3, Hong Chao is going to release it. Hong Chao. Yeah, he's going to release it. Now, the same question. Which would reach the floor first? Which will reach the floor first? Now I don't hear any answer because yours seems confused. Okay, let me give you a hint. Right? Maybe you are thinking this, right? When he released, the book will fall, then this piece of paper will right? Alright? Possible or not? Possible, right? So, your answer should be book first, right? But you cannot say it out. Okay. Wait, don't do this. Okay, now, anybody has a different answer? Any people say paper first? Nobody, right? Nobody. Okay, Hong Chan. Show it to them. By the count of 3. 1, 2, 3. Okay? I thought the piece of paper is supposed to flow, then finish, right? How come both land at the same time? What is wrong? What is wrong? Let me explain to you. Okay? Now, what's the difference between this book and this piece of paper? Of course, naturally, it's the weight, right? Alright, of course, this heavy object will reach down first when we lead it apart. Okay, whereas for this piece of paper, it's light, so it tends to float a bit. Why? Because the weight of this piece of paper is not able to push the air molecules below the paper. Alright? It's not fast enough to push it at the same rate as the book. Okay, now, what happens when we place it in this position? Okay? When we place it in this position, actually, this piece of paper is making use of this book, alright, to float down to the floor at the same time, because there is no gap. Okay? There's no gap between the paper and the book. Alright? So that's why both objects will reach the ground at the same time. Okay? Alright, that's all for my demonstration. Any questions? If no questions, let me ask you a question. What if I do it this way? What will be the result? By now, if you understood my explanation, you should know what's the result. Should be? For a very high point. Oh, then you have to take into account the wind factor and all those things. Then it's very difficult to put out. If it should be the same, the result should be the same. Hong Chan, do you want to turn up? Okay, I will do it. Okay, the proof is that the result should be the same. Right?
Thank you very much, Mr. Thor. Okay, our next contestant is Miss Wee Po Lin from NIE.
Good evening, everybody. Okay, today I'm here to do some magic tricks, and as we know, magicians like to defy physics. So we as physics teachers, we like to defy magicians. So today I'm going to show you a magic trick, and then I'm going to show you the secret behind this magic trick. First of all, I have two pieces of paper. Usually, if you want to balance this piece of paper against the edge of something, you can push it until somewhere around here, it will balance. Okay, if I push anything further, it will drop. So now I have two pieces of paper. I can balance it. Okay, this thing is not very straight. I can balance it somewhere until okay, the magic is not working today. Okay, somewhere like that. Good. Okay, then it will drop. So what happens if I have four pieces and I want to balance it such that this piece, the one on top, such that the piece on top will extend out as much as possible. Okay, you know right, when I balance something and when there's wind, it will drop. So I need some cooperation from all of you. Can everybody stop breathing for the next 3 minutes? Okay, I need 3 minutes of no breathing. Otherwise, my things will all drop. So I'll start to try to balance it again. Hey, somebody's breathing. Okay, don't breathe, huh? Okay, it's balanced. Okay, so what is the secret behind this magic trick? You see, every piece of paper here is the same size, same shape. Okay, and I mark a center line. I mark a center line in the center. This center line, this piece of paper is actually 12 centimeters. So at the center is 6 centimeters. Then I will mark the other one. Okay, when this is 6 centimeters. Use a marker. This piece is 6 centimeters. You know that the CG is acting here at the center. So when I put it at the edge of this box, this CG cannot be over. Cannot be over the edge of the box. But when I put pieces, one on top of the other, I have to find the combined CG of these two pieces of paper. So this is 6 centimeters, this is 6 centimeters. The combined CG is of course somewhere in the center here, which is, this is, okay, this will be 6, this will be 6, and this will be 6. So it will be from here to here, 9 centimeters. And so on. So I can compute onwards. So end of the day, I can have this piece of thing dangling all the way to the edge, but I will have to have a whole big stack of cardboard here. Okay, thank you.
Thanks very much. We can take some questions.
How far of the edge?
What's the maximum protrusion?
You need the protrusion.
The protrusion of the edge of the table.
Okay, let's say I have unlimited amount of cards. From here to here,
Yeah.
another 6 here.
Okay, next.
Sorry. So it's another 12 here, sorry.
Thank you very much, Ms. Wee. Okay, our next contestant is Mr. Wee from Ping Secondary.
Hi. So, let's imagine you are stranded on an island. So you wake up, you need a drink. Okay? So, what are you going to do? What do you think you should do? You should search for water, right? You need boiling water. So, in order to, what, you have your bare hands, you must search around for a container. So, you search and find, you only have only 3 items. Poster, some matches, and a tea light kettle. So, what are you going to do? You need to get the poster, the A3 size poster, and you try to make a box, a paper box. Okay. Now, it takes some skill to fold up the paper, but I will assure you that it's worth the effort. No. Far away. Anybody have water? Okay. Can you pour some here? Oh, okay. More. Much more. Okay. Okay enough lah. Okay, enough. Pour. So you hold it now. So I get my bottle here. Can I help you? Okay. Now, can you please stand up? Can you help me to hold this and carry all the way over there? Be careful, huh? Don't wet on the floor. Okay. So, are you frightened? So, I'm going to light the candle. So for safety reasons, we need this. Okay. We have a candle, light it up. So what we're going to do? Of course, in a while, you need to find a support. Yeah, but let's put it an easier way. We find a support. Okay, next. I'm afraid I stand one second. Okay. How about you? Can you do the honor to place it on top of this plate? Everything okay? Okay. Now, job done. You're safe. Can I escort you back? Okay. Now, so what I've done is that actually I make a box. I'm able to use this box to get some water from water source. I'm actually able to start to boil. Oh. Is it an experimental error? Now, let's continue. Now, so what I'm going to explain today is boiling water. Now, let me explain what happened. Okay. The paper box will not catch fire. The water gets heated up by the candle. Next, the flame hits the paper. The water itself removes the heat from the paper and the water gets boiled. So, what happened to the water? Now, as you know that the water will not be able to get more than 100 degrees, any hotter than 100 degrees Celsius, and all the water will be completely boiled off into steam. In this sense, as it continues to remove the heat from the paper will not burn. And for this case, actually the paper will only burn at 233 degrees Celsius. And that is why, in a while, you can actually fold a piece of paper, but make sure that it is a flat bottom one, no leakage, and after a while, this is the result. This is the result. Thank you very much.
Thank you, Mr. Wei. We can take our question.
This is a known value. It's a known value. For example, it's a known value because there's a famous book. There's a famous book. There's a famous book. There's a famous book on 50 cycles. That is a known value. For example, if you want to know how much this battery is worth, 100 over 160, maybe 160.
Thank you very much.
Thank you very much.
Our next contestant is Mr. Yap Hyung Wee from Yu Hua Primary. Mr. Yap.
Hi, good afternoon everyone. I know when you look at this diagram on the board,
I think you'll be bored. Because Bernoulli's again. Alright. Yes, my preparation is actually on Bernoulli's principle. But however, today's, since you have gone through Bernoulli's so many times, I don't wish to give you nightmare on Bernoulli's tonight. So what I'm going to do, I'm going to change the focus of my lesson a little bit. I'm going to throw the script out of the way. Alright? And what I'm going to do is very quickly demonstrate to you what you have already seen. Alright? This one has my saliva, so I'm not going to call anyone come up. You can't blow the ball out of the funnel. Alright? And second of all, come my two lovely assistants. Of course, one handsome and one lovely. Yeah? Alright? And similar to what you have seen just now. Okay, I'm going to blow air in between the two ping pong balls, and by now you should have seen what will happen. Okay, I think there's a little bit of entanglement here. Another one. Always must have two sets. That's just a learn from NIE, I guess. Alright, come. Yeah. Okay. What do you think will happen to the ping pong balls? Come. Aru, where are you? Aru, what do you think will happen to the ping pong balls when I blow air in between them? They will come together very good. You was paying attention just now. Alright, the two ping pong balls come together. Okay? Now, let me very quickly explain to you, and hopefully you can understand what. Thank you. What is happening, alright, to the Bernoulli's principle, right? Again, my kids over there is going to help me answer some of the questions to check your understanding. Alright, get ready. Okay, when the air comes up here, alright, the air actually rushes out from the bottom. So this place will have a Yang Yue. Will have a lower pressure. Alright, very good. So this is L, lower pressure. You will shock when you are taking photo. Okay, so what about the top here? The air is basically still, alright, slower, and therefore the higher pressure is here. Okay, similar to the two ping pong balls here. Alright, when I blow air through here, the fast rushing air will create low pressure here, high pressure at the two other sides. And we have Bernoulli's principle. However, there is one thing that I think our kids may not be very sure of, because they don't learn pressure in primary schools. They don't know about high pressure, low pressure. And they don't know that when you have high and low pressure, with this difference in pressure, what will actually happen? So this is where I'm going to change my focus of my lesson on now. Okay, when you have high pressure and low pressure, what actually happens? I'm going to demonstrate with a balloon. Okay? Now this balloon here, I believe you all know when we blow a balloon, we are trying to pack in as much air particles into the balloon as possible in a very limited amount of space. Alright? That is pressure. Alright, boys and girls at the back, that is pressure. By packing more of the air particles into a limited amount of space, we create pressure, and that of course means higher pressure than the surrounding atmospheric pressure. Okay? So if you don't know what is pressure, now roughly you should understand. Okay, and what do you think will happen when I release the balloon? What will happen to the air inside the balloon? Razina, what will happen to the air inside the balloon? Obviously, the air will escape or rush out. Alright? High pressure inside the balloon, low pressure outside, the air actually escapes, creating a force and of course also a funny sound. Conversion of energy comes in and everything. Alright, so air actually escapes. And what do we therefore understand from here is that from a high pressure region towards a low pressure region, actually a force is created. A force is created. A force is created. A force is created from a high to low pressure region. And therefore this will then explain exactly why the two balls come together, because of the force created in this different well as for this case, the downward force, which prevents the ball from floating out of the funnel. Thank you very much.
Do you have any questions?
Mr. Jin, I've asked you enough questions. Give you the chance to ask him. To the balloon. Balloonist principle to the balloon. Oh, I showed the balloon to actually explain not so much of balloonist principle, but more of the principle of pressure. Because at primary school, my students, they actually do not know what air pressure is all about. And therefore, using the balloon, I hope using the balloon, I'm able to explain how pressure is related to packing more air particles into a limited amount of space, which will then create a higher pressure. So by using a balloon, I'm able to show that with this particular limited volume, the amount of air particles that can be packed in actually will then increase the pressure inside the balloon. And when I release it, pressure being higher inside as compared to the atmospheric pressure outside will cause the air to rush out, creating a force in the direction of high to low pressure region. And this will then fully explain why the ball actually comes together with an inward direction, inward force, as well as why there's a force being pressed down onto the ball. Thank you.
Thank you very much, Mr. Yap. Our next contestant is Mr. Yeo Chong Hian from Tampines Secondary.
Okay, let's start with this. This is a book. Okay, I would like to ask someone from the audience, probably, okay, come sir, what's your name, sir? Owen. Wow. Okay, Owen, come, use your professional judgment, guess the weight of this book. Come, just take it. Guess the weight of this book. By the way, sir, you are from which school? What's the weight of this book? Oh, sorry, wait. What's the weight of this book? 1 kg. Wrong. Come, sir. What's the weight of this book? 500 grams. Wrong. Okay, now the answer is this is actually 30 newtons. Now in physics, weight is different from mass. Weight is actually a force. It's the force of gravity acting on this book. It's the force that pulls down objects. Anything that has mass is subjected to gravity. So the gravitational force that pulls it down is called weight. So in physics, we talk about mass in terms of kilogram. When we talk about weight, we talk about newtons. Alright, look at this book. This is this book. Now, if I tilt this book, it will be restored back to its original position. Look, I let go, restored, let go. Sometimes it will be restored back to its original position. Sometimes it will topple. Sometimes when I tilt, it will topple. Sometimes it will be restored, sometimes it will topple. Now, to what extent of tilt will cause this book to topple? What extent of tilt will cause this book to topple? So what do you think? I'm sure you know as a teacher. What extent of tilt? No? Okay, now talking about center of gravity. Every object that is regular in shape has a point where it's the center. We call this the center of gravity. Imagine that the entire mass of this object is reduced to one singular point. This singular point is somewhere near the center. We call this the center of gravity. Alright, now imagine this is the book. Of course, I have the law on the table. Now, the weight of the object is a force. We represent forces by lines. Imagine if this is the force. Right, this arrow represents the force that pulls the object down. As I tilt this object, look at the force. The force, which is the weight, will pull back this object. This is the pivot. This point is the pivot. It will restore it back to its original position. However, if I tilt it until the weight exceeds this point, passes out of this pivot, it will cause it to topple. It will cause it to topple because it passes through this point. Now the question is, what if, in theory, what if this particular line of action, this weight, exactly lands on the pivot? What will happen? Come, show me some answers. What will happen? It will stay there, right? In theory, it will stay there. Like this. Before that, I actually tried it out, it works, but sometimes, you know, spur of the moment, if it doesn't work, it's physics. Now, some of you have seen this toy before. This toy, we call it Chinese Fu Dao Wong, right? What happens is when you tilt it, it will be restored back to its original position. No matter how you tilt, it will be restored. You can place it at different surfaces. You tilt it, it will be restored. Alright, different surfaces. Doesn't matter how. This works in the same principle as Mrs. Lee's cookbook. When you tilt it, it will be restored. Why? Because this object has this shape. Same thing, Now the center of gravity slightly lower. When I tilt this object, when I tilt my Fu Dao Wong, when I tilt it a little bit, this point becomes the pivot. Alright, and the weight will restore it back to its original position. Right back to its original position. In the case of the book, what happens is it's not magic, it's just simple physics. You can try this at home, just fill it with water. When it's filled with water, the center of gravity is somewhere here. It passes through, it passes through like that. Right, you will just balance. Alright, thank you very much. Yes, sir. Oh, secret ingredient is yes, the position of center of gravity changes because now in principle, when we talk about any object, you want to locate the center of gravity, all you need to do is you just divide so that the mass here and the mass here is the same. And then you just divide it horizontally so that the mass at the top and the mass here is about the same. So the point of intersection, we usually get the center of gravity. Similarly to the egg, right? It's just actually the area. If you divide it this way, you look at the area here, the area here. Then we talk about mass. It's about the same. Yes, it will be lowered because can. But with water, over here is denser, right? So there's more mass. There's more mass in here. So the center of gravity, which is originally in the center, which is slightly lower. Thanks.
Thank you very much, Mr. Wu. So our final contestant for the day is Miss Cheng, Miss Pamela Cheng.
Alright everybody, good evening ladies and gentlemen. So today I'll also be performing a simple little trick, so I'll start now. Okay, I was actually supposed to have a ping pong ball here, but it's mysteriously disappeared. No matter. Alright, so the thing is, I've got a beaker of water here, and imagine that there's a ping pong ball here. Now what happens is I was to pick up the ping pong ball and drop it into the beaker of water. Well, no prizes for guessing, definitely it's a stay afloat. Yay, thank you. Alright, but what I'm going to tell you now is that I actually have a method of making this ping pong ball, or any ordinary ping pong ball, remain right at the base of the beaker of water without it floating up. Is that possible? I'll show you how to do it. I will need two beakers, one bigger and one smaller. So at the base of the smaller beaker, I'm going to add some super glue, and then I'll attach this ping pong ball to the base and stick it there. So the end result would actually look something like this. So as you can see, no matter how vigorously I shake the beaker or even turn it upside down, you'll find that, hey, it still stays down here. So that's step one. What's step two? Step two basically involves just placing the smaller beaker into the bigger beaker. Carefully. And then what is step three? Step 3 is very easy, right? So just add water. So since it's already been super glued to the base, no matter how much water I add, I can guarantee you that the ping pong ball will stay right here. However, this isn't really a magic trick, right? It's not very impressive, right? So this is what I'm going to do. I will actually be able to make the smaller beaker inside here disappear right before your very eyes. Don't believe me? Okay, I'll show you now. I've got some magic potion here from the Sapa Center. And I'll pour it into the smaller beaker and then let it overflow into the bigger beaker. So it's when the magic potion overflows into the bigger beaker that you see the smaller beaker become invisible from the base upwards. Okay, I'm afraid it's a little bit small, so I've actually prepared this black background. Hopefully it's a little bit clearer. Okay, I'll begin now. Sorry, okay, this is a big beaker, so one magic potion not enough. Don't worry, I'll for another one. Okay, so it's just about to overflow right now, so this is the point where you don't leave your hands, okay? Now try to push it as fast as possible. So now can you see very magically before your very eyes, the smaller beaker is actually disappearing from the line of vision. So can you all see it like this? Okay, yeah. And then I'll put it like this so you can see it. Alright, so what exactly is the science behind this little trick? Okay, this is actually based on a topic called refraction. So what exactly is refraction? Basically, when light passes from one transparent medium to another, say for example, air to water, so this is air and this is water. So what happens when light passes from one transparent medium to another is that the speed actually changes and the light will also bend at an angle. So instead of traveling straight down like this, you'll find that the light will actually bend and travel in this direction instead. So that's why sometimes if you put your leg in a swimming pool, for example, you might find it actually looks a little bit disjointed, although there's nothing wrong with your leg. Alright, so then how does this explain why the beaker in fact disappeared? Well, the thing is, different materials have got different refractive indexes, but interestingly, Pyrex, which is the material that this beaker is made of, as well as this magic potion, which is actually just normal Johnson's baby oil, have got about the same refractive index, between 1.47 to 1.48, depending on which website you go to. Okay, I think the exact one is 1.474, I think. So that's why, because you've got almost similar refractive indexes, when I poured the Johnson's baby into the beaker, the smaller beaker seemed to almost mysteriously disappear within the Johnson's baby oil. So it looks as though there's really only a ping pong ball here. Okay, so with this, I conclude my experiment. Thank you very much.
Thank you very much, Pamela. Do you have any questions?
Because if you actually pour it outside, so you're saying that the smaller beaker inside is empty, right? So if I only pour the Johnson's baby on outside, you find that actually the smaller beaker actually floats up at the top. That's why it's important that the water, actually, the Johnson's baby oil actually goes into the smaller beaker and then from there overflow. Otherwise it just go up like this.
Why don't you just use a simple tool and pull the smaller beaker to the bigger beaker? Like what we have done for the ping pong ball.
So what you're saying is don't use the ping pong ball, just move the smaller one to the bigger one. Yeah, I did that with my intention because I had to use one of the 3 secret ingredients. And I came up with the ping pong ball. Yeah, that was my initial intention.
What if the smaller beaker is of another color, it's not transparent?
Then we will be able to see it. So actually this one, although it's Pyrex, but it's got the calibrations, right? Like the 20 milliliter, 40 milliliters. So actually you can't really closely, you can actually see the white calibrations. It's just that I've lined it with the calibrations of the bigger beaker, so it looks as though it's just the calibration of the bigger beaker. Yeah, so it must be correct, there must be colors, unless you can see it.
Thank you very much. A very big thank you to all our contestants for their wonderful presentations. The judges will now retire to deliberate. The results will probably be announced in about 15 to 20 minutes time. So please stick close by.
I'll keep it short. I know it's very late. By the way, do you all give lessons like this in class? Yes. Great. If we have this sort of generation of teachers, then I hope we'll get more physics undergraduates in NUS. We need more students, so please keep it up. I think I'll just make some general comments, and then later I think Tidfat or Linda will make some comments as to why we chose the winners. It was fairly unanimous, and they'll explain. Okay, so I think on the whole, I would say it's a good effort. I think you all realize that teaching is a performance. We perform every day in front of our students. But somehow or other, I guess many of you feel that performing here in front of your colleagues is a bit different, right? So maybe it's a bit stressful for some of you, but I think it's good to have this, and maybe some of you may even do such things in your schools. Maybe I should start this in NUS to improve the quality of teaching. So I think it's really good. I look forward to this. Hopefully this competition continues. I think some of the key things is while we want to capture students' attention by entertaining them, I guess there's always a balance between to what extent we entertain them and to what extent we get the lesson across. And getting the right balance is really the skill of good teaching. And I think all of us face this, and I think from the many good examples given, we have learned I've learned new tricks and ideas we can put in practice in the classroom. So I'll just like to congratulate not just the winners, but everyone for the good effort, and I'm sure after this session you will bring back ideas and you'll be much better teachers. Thanks.
Okay, we're very glad to see that we'll be giving away also the Judges Special Recognition Award. Okay, the winner being Mr. Jerome Liao Yong Long from NIE. He is recognized for being the best entertainer.
Jerome, I think you stand here while I talk something about you, right? All right, for Jerome, what the judges, what we have discussed just now was we find that your pockets of tricks were very good. I don't know which pocket, right? On the whole, I think it touches the impression on all of us. I think that is one of the other key strength of Jerome, and not because that he is from he's in NIE and I'm from NIE, right? Nothing of that. Just by looking at the eyes of everybody, don't think the other way. Yeah. So for that, is Ballooney's principle, right? Have balls, travel, something like that, right? Okay. I think that's all that we have.
And the second Judges Award goes to Ms. Pamela Zheng Yi Xiu for having the best magic trick on reflection.
Now, Pamela, congratulations. Please stand here. They are going to ask you to do more discipline act. What we have discussed and agreed upon is that her trick, although it's very simple, is based on the refractive index. It actually strikes a chord with the audience. And for students especially, I think they will be very keen, because if you look at the questions asked after that, many of the questions, I mean, of course the ping pong ball is accessory, right? But question asked like, what going to be able to point outside, you know, I think really sets you thinking too. So you know that lesson planning is not fixed. It is very dynamic and versatile, and really I'm asking the same question, right? For example, if it's outside, will it disappear? I think let's do that and see whether you have more disappearing shows. All right? No, thank you.
The third special award is given to Mr. Danny Aoyong Ziwi for having the most excellent performance.
Now, if you look at Danny here from Victoria, no, I have a lot of things to say about Victoria, but I'm not going to say it here. Because I was from Victoria. All right. What I want to say is, okay, again, not like just because I'm from NIE or from Victoria, nothing to do with that. I tell the truth, that's one of the important things, I'm very frank. Okay, Danny's, what we found that you are able to strike a chord again, right across, but the judges also thought aloud. In fact, we discussed whether he has the first advantage. If you look at today's program, a lot of us, we talk about the Belloni's principle, and actually when you blow the funnel effect, all that, of course, he would have the first advantage. So we look at that in detail, discounted the first effect, but with his other strength and delivery, he still managed to come up again. And because of that, that's why he has this outstanding award.
Now, for the prizes, the second runner-up, the cast iron teacher, the cast iron teacher of the year goes to NUS High, Mr. Fong Lei Lin.
It's a walk. Lovely, isn't it? I think we all can go for a walk tonight, right? Okay. Lily, can you please face them? I think everyone likes to see your face clearly, and also that, yeah, you're right. Now, what happened actually for her, that the strength is that we know that you are a very good teacher, or else you would be standing here. But that's the applause, the applause. Your demonstration, you know, remember the rubber band and the paper, and then the amplification of the vibration, and then the sound, and then you go into you didn't go into speaker or microphone yet, right? But you're about to reach that part. Help her clinch this prize that she's holding now, because it touches again our will give us a good impression, and we found that that could actually relate very well in the lesson. Although the blowing and the strumming, the vibration, when you pull it with, didn't really amplify that well in some of them, but and also when some of you tried to blow, right, I think there's one chat here that make the loudest sound, right, somewhere here. So that actually captured the essence of the lesson which you carry out quite well. So that's why she is standing here.
Prize. The wrought iron teacher of the year goes to Mr. Hua Yu Hui from Damai Secondary.
Now you see that Yu Hui, you collect your prize first. And then you can stand very close to me, and I'll stand very close to him, because he's going to give me a treat, right? And teach me how to, the best way to eat food, isn't it? To cut and to slice ultra thin microtome sashimi. Okay, for Yinghui, what we have here for him is that because he managed to, I think he's the only person in this whole today's afternoon's competition whereby he uses everyone except of the secret ingredients, right? I think they were given a list of secret ingredients. Do you use the the ping pong ball? But you use the ping pong ball, but by change I mean saying that it's a fish ball, I remember, right? Yes. My memory is still good, so I haven't started drinking yet, so it's okay. So here, what he has done is that he has shown through the cutlery demonstration a very, very strong, and give us a very strong impression of the usage. For example, the chopstick that is blunt versus the fine tip or sharp tip of the fork, and also the cutting of the knife, whereby you mentioned about having a serrated. I still remember 2 years back, not newspaper, it's television, the Ginsu knife that never need to be sharpened, something like that. So his lesson brought back old memories of Ginsu knife. I don't know whether it's still there, now the Ginsu knife. So with that, I think that was a very good lesson that he had shared with us. Thank you.
Okay, now, the winner, the Iron Science teacher of 2005 is from Kanji Secondary. Yay! Mr. Muhammad Malik in Pahang.
You know, I always save the best for the last.
Okay, I'm glad to be given the last honor to say this, but I think all of us had a very entertaining day where we seen a lot of tricks, a lot of new ideas. But what happened was that this competition was talking about Iron Science Challenge, where you make full use of your secret ingredient. Okay, and so in his example, he made use of the ping pong ball in a very unique way, where he showed the flotation of the balls and how the air pressure and everything. So his focus was really on using that piece of ingredient and explain the concepts that he wanted to convey. And because he was doing it along the way, as he'd ask questions, he was able to captivate people's attention, right? And it became very interactive. No doubt, at the end of his 5 minutes, he actually haven't completed whatever he wanted to do. It was unanimous audience decision to say, can you show me what will happen next? You know, crush the ping pong ball, poke it through. So that was that captivation, and it carried throughout the entire demonstration that he had. And I think with that, he was our unanimous choice as the Iron Science teacher.
Okay, we now have to do a very important thing, and which is we have to thank our judges. And we shall give them maybe the best looking prize, I think, of the day. I'll call upon our Assistant Director, Assistant and Chief Executive, Mr. Clarence Sarasina, to present these gifts to Madam Linda Chua from MOE. Professor Chia Teck Fat from NIE. And Professor Andrew Wee from NUS.
Just conclude, I think next year we'll take up on what Andrew has said, and we'll start the Iron Science lecture competition. On that note, I'd like to thank each and every one of you all for coming and having turned up here today, and for really doing a wonderful job. I think all of you all are winners, to be honest. So I hope you take that, and next year we would love to see a lot more participation. I think we started on an encouraging note, and I'm sure we'll do well next year. Thank you once again.